This is the beginning of several lessons looking at how to differentiate different functions. And by the end of these next few lessons, really by the end of this unit, we should be able to differentiate anything. Any function, any combination of functions, any relation, which means it fails a vertical line test, any combination of things. Any equation, any relationship we've ever seen in a pre-calculus course, we should be able to differentiate. And so in some ways, especially like this power rule we're going to look at, it allows us to differentiate some things that we've looked at before really, really, really quickly. But when we start putting things together and applying them, things can get pretty complex, which is why I haven't been in a rush to jump to these differentiation rules. That's it. Now's the time to look at it. So first, in general, the derivative of a constant is very pleasant. The derivative of a constant is always 0. If a is just some number, if you visualize the graph of just some number, it's a horizontal line. Whatever a is, doesn't matter what number it is, any real number. The graph of y equals 8 is a horizontal line at 8. And so the derivative of a horizontal line is always going to be 0. And so the derivative of any constant is 0. Okay? And with that said, the power rule is something that I find a lot of students kind of know before I get to this. And this is really useful when dealing with polynomials or really power functions. And in general, the derivative of a, again, where a is just some constant, times x to the power of n is the same as a, that same constant, unchanged, times nx to the power of n minus 1. So what does this really mean? This means that whatever power we have here, we can write as a coefficient, and we subtract 1 from the power. And this is always true. And I'll look at some examples of this in a bit. But this is a really, really pleasant and easy to use rule. But we got to be careful. It has to be something in this form. But in general, this is always true. Your power becomes your coefficient, and you subtract 1 from the power. The derivative of the natural exponential function, which is a base of e, is really, really, really pleasant. And this is why a base of e, and therefore the logarithm of base e, the natural logarithm, are so important in calculus. Because as you can see here, the derivative of a times e to the power of x, a being some constant, is a times e to the power of x. It's exactly the same. Now I will say this is only true if you have a base of e. If you have any other base, I will say if you have any other base for an exponential function, the derivative of the exponential function is another exponential function, but it's a different one. So for example, the derivative of 2 to the power of x is not 2 to the power of x. It's a different exponential function, and that's kind of a characteristic of exponential functions. The derivative of exponential functions is another exponential function, but only a base of e is literally the exact same thing, which is really, really pleasant. And that's why it's if you have a choice of an exponential function to use, your natural choice will be an exponential function with a base of e. And so therefore, if you have to use a logarithm, we're not getting to logarithms today, your natural choice will be the natural logarithm. And we'll get to all that later. There's a lot of things to look at. A few notes. These are all the differentiation rules I want to look at today. A few notes that I highly recommend you write down are these common mistakes. And the first one is what I was just mentioning. The derivative of a to the power of x is not a to the power of x. Again, this is only true if that a is, if that a is e. Okay? So like I commented on, please don't think any derivative of any exponential function is unchanged. It's only if the base is e. And as well here, what if you do have a base of e, but you have a constant right there, e to the power of ax? This is not the same as e to the power of ax. Again, so what's the difference? The difference is right here, there was no coefficient in front of the x. It was just x. So as soon as there's anything else going on in there, it's no longer quite this simple. And we'll get to all these things. Again, there's a lot of things we got to look at. But if you have just, again, e to the power of x, and you're differentiating with respect to x, nothing changes. All right, so those are all the rules we're going to look at today. Let me just have one question to use this. And so here I have a function, and it's this rational function, 2x to the power of 5 minus 5x squared plus 2 all over 2x. Okay, what I want to do is I want to find the first, second, third, fourth, fifth, and sixth derivatives of this function. Okay, and I will say, Sometimes, perhaps just the sight of this looks daunting. And depending on the function, sometimes finding this many derivatives is horribly, horribly daunting and messy, and things get out of hand. But quite often things go the other way. Things keep getting simpler each time. And quite often it's just every derivative is just kind of something similar. We'll see. It's hard to assume until we actually try it. That said, before I differentiate anything, first of all, I have a quotient here, and I have all of this divided by this. And either, if I want to differentiate this, I either have to learn about something called the quotient rule, which is not part of today's lesson, or I have to change it out of this form. Anytime I have a quotient, I have one function divided by another. The derivative, I can't just find the derivative of the numerator divided by the derivative of the denominator. That will be wrong. So right now, I have not taught you enough at this point to differentiate this in the form it's in. But I can change the form. And quite often, in fact, very, very often when dealing with functions and you're differentiating them, quite often we want to change the form of them before we start differentiating to put into a form that's more convenient for us. And so let's start with f of x. What I want to do first is I want to write this as three separate fractions. I want to write it as 2x to the power 5 over 2x minus 5x squared over 2x plus 2 over 2x. And the point of doing this is that I'm going to get 4 separate terms, and I can differentiate each of those 4 terms separately. I don't have this big quotient anymore. For example, 2x to the power 5 over 2x, same as just x to the power 4. Minus, I have just 5 over 2x. Plus, I have 1 over x, which is great. However, I can now use the power rule to differentiate this. I can use the power rule to differentiate this. I haven't yet taught you enough how to differentiate 1 over x. If you look back at the rules directly, none of them I mentioned directly relate to this. But indirectly I have, because 1 over x is the same as x to the power of negative 1. Understanding and using negative exponents becomes so crucial in this course. So this is the same as plus x to the negative 1. And now, I haven't differentiated anything. Really, I've done a bit of grade 10 math. I have, taken a fraction, broken up the terms, canceled out some variables, used negative exponents. Now, though, what I have here is really, really easy to differentiate using these rules I taught you. So there is still f of x. Okay, that's f of x. So now let's find f prime of x. So the derivative of x to the power 4, the power becomes a coefficient, and I subtract 1 from the power. That's it. So the derivative of the derivative of x to the power 4 is 4x cubed. Done. Minus the derivative of 5 over 2x. Well, you can imagine there being a power of 1. So you can imagine I put a little coefficient of 1 right here. Actually, I'll put the 5/2 first. So times 1, which is kind of silly. I'm going to erase that. Times x to the power of 0. That said, while it's not wrong, x to the power of 0 equals 1. And so really, I have negative 5/2 times 1 times 1. So in the end, all I have is negative 5/2. And another way of looking at this, of understanding why the derivative of negative 5/2 x is just negative 5/2, is if you look at just this term in isolation, that's a linear function. That's a line with a slope of 5 over 2. And the slope of a line is the same as the derivative of the line. And so, it actually makes complete sense. This is just negative 5 over 2. And then for the last one, using the power rule again, I want to bring the exponent becomes my coefficient times x to the negative 2. And there's my first derivative. That said, only thing what I can do to clean it up is I can just write this as 4x cubed minus 5 over 2 minus x to the negative 2. And keep in mind, x to the negative 2 is the same as 1 over x squared. And there's nothing wrong with me writing it like that. But if I write it like this, it's actually more convenient for me to differentiate, which is what I want to do right now. And so we'll find when in terms of differentiating, writing fractions, writing powers with negative exponents is actually quite pleasant, because we can just use the power rule. There's my first derivative in 2 different forms. Let's find the second derivative. Okay, second derivative. So first, let me differentiate 4x cubed, and that becomes 12x squared. Again, brought the exponent times 4 is 12, and then subtract 1 from the exponent. Minus 5 over 2 is a constant, so the derivative of a constant is 0. So that's nice. And then next, minus -2 times x to the -3. Maybe I'll just kind of highlight how all these are changing as I go from one derivative to the next. And so keep in mind, I'm subtracting a negative, so I'm just going to write this as I'll change that to a plus. All right, that's my second derivative done. Clearly, I don't need that plus 0 anymore, so let's go to my third derivative. So again, coefficient of 12 times the power of 2 is 24. Subtract 1 from the exponent. I have just 24x. I don't need to deal with that 0 anymore. And so for the 2x to the -3, when I differentiate that, I get -6x to the -4. All right. Notice, actually, as I'm differentiating, each time it's not actually getting any more complex. The fourth derivative, and I will say, at some point it probably gets silly drawing all these little apostrophes. So usually at some point we just put a number, but I'll just put 4 here for now. The derivative of 24x is just 24. And the derivative of -6x to the -4 is plus 24x to the -5. All right, almost done. I want 2 more derivatives. The fifth derivative. The derivative of 24 is 0. And the derivative of 24 times x to the -5 is -120 x to the -6. And so by the time I finally get to the sixth derivative, I'm down to 1 term. And so it's just a derivative at this point of -120 x to the -6. Well, -120 times -6 is 720 times x to the -7. There we go. So while I just found 6 derivatives, because I could use the power rule for every single one of these, it was really, really quick. But notice the first thing I did, actually, my first few steps, if you look at the top, were taking this equation that I gave you and putting it into a different form. And we'll end up doing this a lot. In fact, one of the most common mistakes that students make, or I shouldn't say make so much of a mistake as something I don't recommend, is that they just automatically look at an equation and start differentiating it as it is. Because I will say by the end of this unit, any equation, any form, you should be able to differentiate as it is. But quite often you have something that if you leave it, if you don't do any adjustments to it, you make your life way more difficult and way more messy. That's not really a new idea. If you think back to pre-calculus 12 when dealing with transformations, quite often you have to take the equation and put it into a form that was more useful to you. And similar sort of idea here. All right, so that said, that's it.